In this session, I would like to talk about machine instructions and addressing modes. Before going into details, first of all, we start with the small, keywords I can say, which are related to our subject. That is, what is byte addressable system? What is word addressable system? Let us begin with that. So, in your system, if in your main memory, if every byte is numbered, that is called byte addressable system. In your system, if every word is numbered, especially I am talking about main memory, then that is called word addressable system. So what is word is, generally it's a logical unit of data on which you are going to do the operations. Typically the word size will be 32 bit. Okay. So nowadays in modern architectures, the word size is 32 bit. Okay. That means all your machineries will be designed such a way that 32 bits of the data will be transferred from main memory to registers. Otherwise 32 bit data may be added in that way. Since you have 32 bit registers, and one more thing you ask yourself, what are you going to do with your computer? What are the typical and basic operations your computer is going to do? One is addition, right? Subtractions. Otherwise moving the data from, right, so your registers to main memory. Otherwise moving the data from main memory to registers. These are the typical operations you generally do, right? So in all that operations, what is the size of the data you are going to take? That is called word. Typically, that will be decided by some of the experiences. So currently the modern computers are using word size as 32 bits. Okay, remember it. It might be 64 and that is none of our business. Okay. So we can negotiate, not a problem. We can say 32, otherwise 64. It's not standard, like we can't say that always it is 64, always 32. It depends on your processor and architecture. So but majority of the systems again will have word size as 32 bit. Okay. Now we'll come to this big endian and little endian notation. So what is big endian and little endian? I will tell you. Before that, let me ask you one question. So what are you going to, you are going to store data in your computer, right, in main memory. So we are going to talk about that. When you are storing your data in main memory, you can store that in two ways, and I am assuming that word size is now 32 bits, that means 4 bytes. Okay. So when you are storing, generally already I told you the basic operation from now onwards in words, right? Example, let's say you want to store one word, okay, in your main memory. I am assuming that my system is byte addressable. So this is your typical word W, let's say. Okay. Now if it is 32 bit size, then it will occupy, otherwise it will take 4 bytes, correct? Now see, byte 1, byte 2, byte 3, byte 4. Now you know that in byte addressable systems we are going to number the bytes, right? How you number them? Do you number them like from left to right? Otherwise right to left is the question. If you number them from left to right, that means least number if you give to left side, leftmost byte, then we say that is big endian. You see here. Otherwise I can say this is most significant area, right? Most significant bits. These are all least significant bits, right? Least significant byte otherwise. So you have 4 bytes, 1, 2, 3, 4. Now if you imagine like this, so most significant byte gets 0, least significant byte gets 3, that means highest number, then we say that is big endian. Okay. Now in little endian, the order will be reversed, that's it. So if this is the case, so this is, let's say, least significant byte, this is most significant byte in a word. There are 4 bytes in a word, and I am assuming that our system is byte addressable system. Then, so if you number them like this, least significant byte to most significant byte, okay, 0, 1, 2, 3, that is called little endian model. Of course, these two are trade-off. You can either use big endian or little endian, doesn't matter. Okay. So we can't say that we have to use only big endian or little endian. So these two are like left and right hands to you. Okay, anything you can use for some purpose, right? Unless you are already you have practiced with that, right? Otherwise, then left and right there is no. This is the first time you are using your hands, then anything is fine, right? Similarly, big endian and little endian. Now see here, 0, 1, 2, 3, then 4, 5, 6, 7. Then the third byte will be numbered like this: 8. The second byte is 9, third byte 10, 11 in that way. Here it would be, the next word will be numbered like this. It contains 4 bytes. Then that would be, right, 8. 9, 10, 11. This is the difference between big endian and little endian. Okay. So now we will start with machine instructions. This is enough, this foundation is enough. So let me ask one question, why you require machine instructions? For that only answer is, you have a computer and you know that this is a processing machine, correct? It is going to process some things, right? That means you know that it is going to do additions, subtractions. It has some functionality, we know that, right? It has some equipment and we are going to use it and we are going to do some operations, otherwise we are going to perform some tasks. For that we have to write a program, right? According to von Neumann concept, von Neumann is, I can say the pioneer, pioneer of this terminology, otherwise pioneer of, otherwise defining computers. He said what, he said use stored program concept. He introduced stored program concept. That means write a program and store it and execute it. That is what stored program concept. Now still that principle works. Still people follow the same model, correct? Whenever you write a program, whenever you execute, what do you do first? You write, correct? Once you write it, you store it. That means your program's instructions will be stored. Then after that they will be executed, correct? So that's why that is called stored program concept. Now still we are using that. In 1930s I think he proposed it, but still it is applicable. Now what is machine instruction is, your computer whenever it is designed, so the people who designed it, they gave us some interface, okay? That interface is like this, instruction set architecture. That means they have created instruction set architecture. Now this is your computer, it performs some operations and this is a human being. Now this human being wants to communicate with this hardware device, right? Then so let's say this computer can perform additions and subtractions and whatever. First of all we should know it, then only we can use it, right? So I can say that this computer is going to have some, perform some operations. It is going to have some services. We have to use it. For that, there should be an interface. So through this interface we are going to, let's say, so this is an interface which is going to provide us information about what are the actions your processor can perform, like addition, subtraction, right? So load, store, we will be seeing one by one. Don't worry. Assume that these are the operations your computer performs. Then, so this instruction set architecture is nothing but it is an interface between user and computer. This computer says that now after studying this instruction set architecture, by seeing these instructions I can understand that, oh, my computer can do addition, subtraction, load, and this instruction set architecture provides you how to, that means syntax of the operations. That means if you want to do one of the operation of your computer, you have to mention the syntax, right? So instruction set architecture is going to take care of that. Now the instruction set architecture says that, my dear user, this is the syntax to do the addition. This is the syntax to do subtraction. Based on that we are going to do it. Now one more advantage of this instruction set architecture is, it is going to provide, abstraction. What is that abstraction? I will tell you. Tomorrow, so this computer, let's say, got some additional functionality. Apart from addition and subtraction, let's say it is also providing multiplication. Then that functionality can be happily added here. Then that will not disturb us, right? Still we will be happy to get one more functionality or one more service, right? So that is the abstraction which is going to be provided by instruction set architecture. Second thing, that means one more thing we are not worrying, that is how this multiplication is performed. Really Booth multiplication algorithm is used, otherwise sequential multiplication algorithm is used, otherwise Booth modified algorithm is used, doesn't matter. Unless if this multiplication function is eliminated from the list. If really this multiplication syntax I have, that is enough. So whether Booth multiplication is used or sequential doesn't matter, right? That is one more thing. Now in instruction set architecture, so we are going to have machine instructions, okay, or instruction set. That instruction set is going to contain machine instructions. And one more thing, So we are not going to study at this moment how these machine instructions are going to be implemented. So that is other end. You can see two ends. One is how this addition, subtraction, load, everything are implemented. Of course, we have seen how addition, subtraction can be implemented. But how load, store, multiplication, everything, of course multiplication also we have seen some details, but complete details like how this addition, subtraction, load, everything will be implemented, we are not studying at this moment, but we would like to focus on how that instruction set can be used, otherwise how this machine instructions can be used to effectively solve some problems. Okay, so that part we are going to study, that is nothing but a topic called machine instructions and addressing modes. Let us study that. Now, what do you think about these instructions? That means, what are they going to provide, right? If you broadly classify them, so they can be classified into four parts. Any instruction generally, can be used to, transfer the data between the memory and processor register. That is one functionality your instructions are going to provide. Okay, that means using the instruction, we are going to transfer the data between memory and processor registers. Okay. Second thing, we are going to do arithmetic. Sometimes we will be doing logical operations, right? You will be checking the conditions like, X and Y kind of stuff, right? So that is logic unit. So finally, arithmetic and logical operations we are going to do. That means we need instructions for that. And sometimes just think about C programming. In C programming, whatever you want to achieve, the same thing you will be achieving using this machine instructions, correct? Because every high level language program will be converted to this machine level language. So whatever the functionalities you are going to achieve through high level language, first of all, they should be achieved through machine language. Example, some functionality is not possible with machine language, then how can you achieve through high level? Because every high level instruction will be converted to some of the machine level instructions. That's why, so whatever comes to your mind about high level language instructions, they will be applicable here also. Now, in that way, if you think, you will be using, some kind of flow, right? That means we will be writing a program such a way that, we suddenly jump from one instruction to another instruction, and take the decisions based on the conditions, right? Through the program, like if, while, everything. So program sequencing and control can be done here also. Okay. So finally, we are going to write a program here also. That is the main thing, right? That's why it's a stored program concept. First of all, you will be having a program. Don't forget about that. So that program contains now machine instructions, because we are talking about low level details now. So we are going to write machine instructions to perform a task program. That machine instructions either should transfer the data from memory to registers, otherwise registers to memory, otherwise they should perform arithmetic and logic unit operations, otherwise the program should be sequenced. That means your instruction should sequence the program, correct? Maybe they should control your program's flow, right? Like jump instruction, correct? Otherwise branch on 0, branch on non-zero. In that way there are so many things, we will study that. All these instructions are going to take care of this program sequencing. Now the final one, IO transfers. That means once the data is prepared, you want to see it on the output panel, right? Maybe you want to see it on monitor, right? For that, data should be transferred to a IO device called monitor. Similarly, first of all, your program has to take the input. Who will give the input? User. How user can be connected through this program? He will be connected through keyboard, right? That means if you want to give input, then you have only one device, two devices. One is mouse, second one keyboard, right? Major devices. Of course, I'm not saying that we have only two, but through generally keyboard and mouse, we are going to give the input. So we need, again, everything is done through machine instructions. If you don't have machine instruction which supports sending the data to program through keyboard, if there is no such instruction, then you can't perform any such operation, right? That's why from now onwards you assume that everything is possible through only instructions. That means if you are giving input through keyboard and if your program is taking, definitely there might be some instructions involved, right? Which communicates through keyboard. That means so keyboard's input will be taken through some instruction. That's why there will be some instructions in your machine's architecture set. Okay, so that instructions are also important. They are called IO instructions. We will be studying that also. So finally, so IO transfers are going to be done through that IO instructions. Now finally, so the major operations, otherwise all your instructions, otherwise their functionality can be classified into 4 parts, right? Let us summarize quickly. Data transfer, second one arithmetic and logic, third one program sequencing, the fourth one IO transfers, right? IO transfers also very essential. Now we will be studying one by one, like in this session majorly we will be focusing on these three. So this IO transfers we'll see later. Okay, yeah. Now we will see one more classification of instructions, that is RISC instruction set and CISC instruction set. What is that? I will tell you. RISC is nothing but reduced instruction set computers, and CISC model computers are called complex instruction set computers. Sir, what is, we did not understand anything. I am going to tell you. So your computers are classified based on their architecture into 2 parts. One is RISC machines, second one CISC machine. Sir, what is RISC machine and what is CISC machine? RISC machine is a machine whose instructions are generally, in one line I will tell you. Generally in RISC machines, the instructions are very simple. Okay, we will see more details. Generally here this instruction set is little bit complex. Okay, so sir, what does it mean? Like my instruction set simple means? So whenever I say instruction set is simple, then it follows generally a load store architecture. Okay, RISC computer generally follow load store architecture. Slowly you will understand how it will become simple. I did not answer why RISC computers are simple. First of all, try to understand the definition of, otherwise the properties of RISC machines, so that you can understand that they have simple architecture. Okay, now this is all about instruction set. Okay, so RISC computers and CISC computers are differentiated through instruction set. Now example, let's say your all instructions follow a load store model, where only through load and store you are accessing the main memory. This is your main memory, and all the memory accesses are only through load, and majority of course, otherwise there might be some exceptions, but in theory, so we say that a RISC instruction set, whichever computer follows RISC instruction set, so on that only the memory access will be possible through load and store instructions. We will see load and store instructions in a detailed way, but I will tell you what is load instruction and store instruction. So through load instruction we are going to take the data from main memory to CPU registers. Okay, whenever you want to take the data from main memory to some temporary register or general purpose register of your CPU, then we say that that is load instruction. The purpose of store instruction is you have some data in register and you would like to store it in some main memory, that is store instruction. In this too you can see there is one main memory access, correct? So why we are stressing that point? What is so speciality? What is so special about main memory access? Generally, so your main memory access takes significant time. Okay, that's why we have to reduce that time. That is one of the major goal of this computer organization. Understand? That's why we organize the main memory into cache, and we know that stuff, right? Secondary memory, everything. We will see that details. But here you remember, generally main memory access time is significant. Okay, we have to reduce it. We have to skip as many memory accesses as possible. We will do that. So in RISC machines, all the memory accesses, whatever which are costly, they will be done through only load and store instructions. Okay, now there will be arithmetic. Whenever you are doing arithmetic, for that we use arithmetic instructions or logic instructions, right? Arithmetic instructions and logic instructions, this is second property of RISC machines generally. So they will not be involved, okay, machine otherwise memory accesses, remember it. Now only load and store will use memory accesses. Arithmetic and logic operations are not going to access the memory. They will be performed through registers. That means if you want to do addition, then you have to use CPU registers like add R1, R2. We will see the syntax later, but to add or subtract anything, we will be using CPU registers. That is the way the machine is designed. Then we say that is RISC machine. Okay. Now in complex instruction set computers, so we will be having additions and subtractions of main memory registers, otherwise main memory operands directly. Okay, that means we might do like this: add memory 1 comma memory 2, where memory 1 memory 2 are nothing but the memory locations where you have operands. And by the way, operand means so where you are going to perform the operation. When you are doing operation like addition, you need operands, right? We know that basic concept. In data structure also we have studied. Operands are going to be used to perform an operation, right? So here to perform operation, add operation, we are going to use two operands, and they might be memory locations in that way. So such kind of instruction set. Example, you have instructions where you have arithmetic and memory access in one operation. Such kind of instruction set is called complex instruction set architecture. Okay, so we will be, so how to understand it, sir? Like, what's big deal? How these two are different? Here either we are accessing the memory, otherwise we are performing arithmetic. But here you are performing arithmetic followed by accessing the memory, right? So here mostly what happens, because of that, complexity will be increased. That means, so some instructions take lot of time, some instructions take very less time in that way. Okay, so uneven time. When the instructions takes uneven time, then the design will become, and one more thing, to implement this kind of things, so the architecture will become complex. Okay, the design will become complex, but implementing RISC kind of architecture is simple. So whenever your architecture is simple, then you are going to get the benefit. Okay, so RISC computers are going to get the advantage over CISC. You will be understanding that after learning pipelining. So in pipelining concept, I am going to explain you again why RISC kind of machines are going to get the faster, otherwise better function. So better time. That means why RISC computers are going to get the advantage of pipelining. We'll see. What is pipelining? You don't know, right? So using the pipelining, we are going to improve the execution time of the programs. For that, RISC kind of instruction set is I can say suggestible, not CISC. So CISC kind of architectures are not going to get advantage thoroughly like RISC machines. Okay, that is a difference. Now you understood what is RISC and CISC in a basic way, right? So now we'll see first RISC kind of instructions. Let's recall what is RISC properties. Whenever an architecture is, or whenever your machine is RISC machine, that means it is implementing reduced instruction set, right? So in that reduced instruction set, either you are going to perform arithmetic logic, otherwise you will be accessing the main memory through load and store. Okay, now we will see the details, more details about this reduced instruction set. Okay, so we'll see one by one.